Hello everyone. In the previous videos, we showed what is a decision tree and how is a decision tree partitioning the feature space into different subsets. In this video, we will consider how we can determine the best split. So if we want to split a certain node into two child nodes, what is then the best way to split it? And we start with a regression problem. So the target variable y is a quantitative variable. Then if we have a prediction y hat, then we use the squared difference, y minus y hat squared, to quantify the goodness of your prediction. And the question is, what is the best split? First of all, if we split, we use a standardized binary split. It means that we only split along one variable. So we have to pick x1, x2 until xp. We have to pick one variable to split the node. Once we determined which variable we will use to make the split, we have to determine the c to determine the splitting rule. So if we use a variable xl to split a node, then we will have two regions. We have xl smaller than c and xl larger than c, and we have to decide what is this value c. Consider the node rt. Then what we will do is we will start in rt and split this node in two parts. We have rt0, the left child. We have rt1, the right child. And rt0, rt1 are defined in this way. If we have observations in this node, then we use the prediction lambda 0. And if we have observations in this rt1, we use lambda 1. If you then look at this sum here, it's a summation over all the observations in our datasets that belong to this left child. And we observe the yi, but we use the prediction lambda 0. So this here is the sum of squares of rt0. In the same way, this here is the sum of squares of rt1. Putting them together gives us the sum of squares of the node rt that is split in two parts, where I use lambda 0 and lambda 1 to make predictions in each of the subregions. And this sum of squares depends on L, C, lambda 0, lambda 1. So what we need is, we need to minimize that sum of squares by searching for the best L, the best C, the best lambda 0 and lambda 1. So the best way to split the node RT is by solving this minimization problem here, where I first take a minimization over L and C. So L is the feature variable that is used to make the split, and C is the number that determines the splitting rule. So once I determine L and C, I can split my node RT in RT0, RT1, and then I look for the lambda 0 and the lambda 1 that are used to make predictions in each of the nodes by minimizing these inner minimization problems. And why do we use two minimizations, first over LC, then over lambda 0, lambda 1? Because this minimization problem here, so given L and C, we know that the best way to predict inside RT0 is by the sample mean. So if you just look at this minimization problem here, you can solve it by taking the derivative, putting this derivative equal to 0, you will find the sample mean. And the same holds for this second minimization problem. Given that we know the variable xl that is used to split the node and the c that is used to determine the splitting rule, the best prediction in RT1 is the sample mean. So we can solve for lambda 0, lambda 1 in an analytical way. The other two, L and C, need to be solved in a numerical way. In your slides, you will see that I will work out an example where I solve this problem numerically using R. And you can find the R coding of this example in a separate video. Let's now have a look at overfitting when we deal with decision trees. So by now, we know that a decision tree is partitioning the feature space into subregions, and we know how we can determine the best way to split each of the nodes. So a decision tree will keep adding nodes and leaves in order to improve the training error, to reduce the error. However, if there are many leaves, you have many subregions, then at some point you can almost perfectly match the data. In the most extreme case, you have just a leaf for each single observation. So that would mean a perfect fit for the training data set, but of course that results in a very high variance for your decision tree, meaning that if you change the data, you directly get a very different decision tree. So the larger the tree, the larger the variance of your predictions. So it means that if we increase the tree, if we add more and more leaves, you get a better fit of the training data set, but the cost is that you get a higher variance. And we know that there is a bias variance trade-off. It means that we need to balance goodness of fit and the size of the tree. We want to have a goodness of fit, meaning we want to have large trees, but at the same time we want to reduce the variance of our decision tree, which means that we want to limit the complexity of our decision tree. I can go back to my initial example with population and sales. And I can fit a tree, and I find a tree with 4 terminal nodes of 4 leaves. It's a relatively small tree. Let's now again fit a tree on the same data set, but now I add this control vector where I say that the minimum deviance that you need to have to continue splitting the nodes is very small. It means that we keep adding nodes to our decision tree. And what we end up with is a tree with now 93 nodes. So now we have 2 trees. T0 is a small tree, T1 is a large tree. For T1, so the large tree with 93 nodes, this figure shows the fit of your training data set. And what you see is that if you look at the observations, which are the circles, and you look at the predictions, which are the red dots, they're almost the same. The decision tree is able to almost perfectly replicate the training data set. So we have a almost perfect goodness of fit. However, if we use a test data set, so a new data set, and we use our trained model that had a perfect fit on the training data set on this test data set, we see we do not have a very good fit. So it seems that our model performs very well on the training data set, but does a bad job on a test data set. And that is what we call overfitting, and it is caused by the high variance of the decision tree. What I do now is I create many trees, each with a different size. And I look at the test error and the training error. If you look at the training error, we see that if the size of the tree increases, so if you add more and more nodes, your training error will always go down. So if we only look at the training error, large trees are always better. But if you look at the test error, you see that there is a minimum here. If we have trees that are too small, you have a large training error, test error, because you do not fit the data very well. However, if your tree is too large, although you have a small training error, you still have a large test error because you are overfitting the data. So it means that we try to balance small and large trees. We want to have trees which are not too large but also not too small. And how you can do that in R, for example, that is what we will see in the next slides. We first need to define what is a subtree of a given decision tree. So a decision tree looks like this. We have nodes, and these nodes are then again subdivided in new nodes. So if we have a tree T here, then T prime is a subtree of T if there exists a node RT prime such that this node is a node in our tree T, but also serves as the mother nodes of another tree. And in this case, we can look at this red tree here. Then you see in this red tree, RT prime is the mother node. If we have a tree T and a subtree T prime, we can look at a pruned tree that I call TP1, which is the initial tree T, but now we prune, we subtract this T prime tree here. So we take that out and we end up with our new pruned tree. So by pruning a tree, you make the tree smaller. You take out a subtree, meaning that your initial tree becomes smaller, has less leaves. So here we have another example. We have a root node R0. We have our whole tree T, and this red part here is the T prime. We can then prune our tree by taking out this T prime subtree, and then we end up with this new tree, which is a pruned tree, a smaller tree, because I take out a subtree. We can continue the process of pruning because now we have again a tree and a subtree here. So we can say, well, let's subtract the subtree from the initial tree and we end up with a smaller tree, a pruned tree that is here. So in this example, we started from a tree T with 5 leaves, then we took out 2 subtrees, and we end up with a smaller tree with only 3 leaves. And the black tree on the previous slide, that's what we call TP2, that is the pruned tree. First, we prune it by subtracting T prime, and then we subtract it by pruning T double prime. And T prime and T double prime are both subtrees of the original tree T. However, if I look at the pruned tree, it's the original tree T minus these two. This is not a subtree of our original tree. So I subtract 2 subtrees, but the subtrees together do not form a subtree of the initial tree. Let's now have a look how we can avoid overfitting when building a decision tree. So assume that you start building a full decision tree. It means that you split in order to decrease the sum of squares. And for example, you use as a stopping rule a minimum number of elements in a node. You say we keep splitting until we have 5 elements in a leaf and then we stop splitting. Then we have a very large tree because we only look at goodness of fit, and improving the goodness of fit means growing large trees. However, then we will say if we have a pruned tree T prime, so a smaller tree than the original tree T full, we can look at the cost complexity R alpha. So what is that? The cost complexity is this first term here. In my T prime, I have this number of leaves. So inside each leaf, I look at the sum of squares and I look at all the leaves. So this is the total sum of squares of my pruned decision tree. Because I prune the tree, I make it smaller. My sum of squares of my pruned tree, so that first term, is larger than the sum of squares of the full decision tree. However, I also add another term that measures the complexity of the tree. So for a large tree, we have a higher complexity, so that term should be larger. So that term is alpha times the number of leaves in my tree. So if we have a large tree, then you have a small goodness of fit, so a small sum of squares, but a large number for the complexity. Whereas if you prune the tree, you make the tree smaller, so you decrease the second term, but you increase the goodness of fit. Then in order to find an optimal tree T star, we search in all possible pruned trees and we take the tree that has the smallest cost complexity. If we put the alpha equal to 0, then R alpha only measures goodness of fit, no complexity, then your best tree is a full tree, because then the larger the better. If we take alpha larger and larger, then optimal trees are small trees, with only a few splits and a few leaves. Note that cost complexity measure, R alpha, which is goodness of fit, sum of squares, plus complexity, is very similar to the lasso model. That was also a model where you have goodness of fit that has to be balanced with the complexity of your model. In this case, it was the size of your regression parameters.